Okay, looks like we're live on YouTube as well. So hey everybody, and welcome back to another session of Fastbook Reading Group. And I've got a couple announcements today, so just give me one sec. Let me just get things sorted. So I think it's all looking good now. I think YouTube is working as well. So let me just do a quick. Should be fine now. Okay, and then you can hear me on Zoom. All right. So let me switch back to sharing my screen. Okay, so you should be able to see chapter 15, Application Architectures Deep Dive. And I'm just going to switch to my complete screen. Please let me know in case you can't see my screen anymore, because I think I've just changed something. Should be fine now, though. I've got a couple announcements today. So just this morning, I've been thinking a lot about this lately. Is like, what is a good time to end Fastbook Reading Group? And what is a good time to what is a good time? And there is no good time, but I think now is still a very good, now is still like, I won't say like, now this chapter 15, after this chapter 15, I think is where we can end things, and we can call this like the part 1. And the more that I think of it, the more that I agree with this decision. And I even had I had a chat with a couple of my colleagues before joining this Fastbook session, and we all kind of agree that it's okay to wrap up things here. So for those of you, it would come as a news to all of you, but today would be the last Fastbook reading session. And as part of this reading session, we're going to cover chapter 15, and we're going to look more into CNN Learner. We're going to look into a bit of UNet, and we're going to close off things from a computer vision perspective. And before I proceed with chapter 15, I just want to say, like, I want to explain the decision for doing so. And in doing that, I think I want to share that what's next. I was just having a look at all the chapters at what's coming. So we've got we've got a chapter on SGD. This is basically explains like optimizers, explains momentum. And for those interested, I've got a blog post on this as well. So if I go to my personal website, and there should be one on optimizers. Here it is, Adam and Friends. So if we go into this blog post, you will see, like in this blog post, I've introduced everything from scratch. Basically, I've re-implemented PyTorches, SGD, RMS prop, Adam, and basically even momentum. So SGD with momentum, and Adam has that already. So if you go and there's like lots of resources and credits, and there's lots of places where you can learn more about optimizers. So I think this blog post would serve as a good place, because I won't have anything new to share apart from sharing this blog post with everybody. So I'm just going to post this in the chat. And before we proceed further, if you go to 1db.me/fastbook15, that should take us to the community weights and biases. This is the forum. So let me paste that link over here as well. So this is, I'm just going to post here. So if anybody's actually talking about, oh, hey, Sam. If anybody's talking about, please use the forum as the place to comment, because I'm not looking at the Zoom chat, and I'm not looking at the YouTube sessions. Sorry, the YouTube chat. But let me just quickly post this here. This is the blog post on optimizers. So if you have a look at this blog post, you'll see like everything's been explained nice and easy. So that covers off pretty much chapter 16. And then what we're left with is chapter 17, 19, and this one, which is CAM. So in chapter 17, there's foundations, which is pretty much PyTorch from scratch. So what you'll see in this is like modeling a neuron, or matrix multiplication from scratch, or you'll see element-wise arithmetic, and there's like broadcasting. There's all of these things. There's all of these things that are completely PyTorch specific. And for those interested in learning about these things, I'd like to direct you to this another event that my brilliant colleague Sangyam Bhutani is hosting, which is the PyTorch book reading group. And in this one, this book was written by Thomas Wieman, and in this book, I know there's like a complete chapter on broadcasting. So if in FastAI is like one section of the chapter, there's like this complete chapter, and this book reading group would serve as a great place to learn more about Python. So foundations chapter is basically PyTorch. So I'd like to direct everybody again to this. If you come to community.1db.ai, so if you go at this community.1db.ai, this brings you to the Weights and Biases forums. And from there on, if you go to community events, which is right here, and there you can see like all the different events that are currently on. And if you go to PyTorch book reading group, this will land you to Sangyam's reading group, which is learning PyTorch and learning everything about PyTorch. So that's a great place. And then again, skipping CAM, because that's just the paper, and it's like CAM is more about like highlighting or like checking what the model is learning. So that's a great place, but I could cover that off as part of the paper reading group in the future. And then you have a FastAI learner. And in this one, it's pretty much creating everything in FastAI from scratch using PyTorch. So again, as long as everybody has interest in learning PyTorch and you have your foundation set for PyTorch, then we can come back and do this as Sayam and I have decided that we're going to do this as a guest lecture, like both of us are going to host one together. So when the PyTorch reading group comes to a point where everything that's been explained in this chapter has been explained, like data loaders, data sets, or like all these different things, what's an NN module, once all of these things have been explained, then Sangyam and I will probably host a session where we explain like how to build a FastAI learner from scratch. So I think like what I mean to say is after chapter 15, there's no new concepts that I can teach you. There's nothing deep learning. Well, there's like this is a good platform, and where I know most people like and myself from the FastAI community, where I know most of these people, we kind of ended at a similar platform. So when we did the part one FastAI course, there's usually a gap of 3 months between part one and part two. And that gap was actually a blessing because in that gap, everybody who's part of the group can now spend their own time learning their own things. So if you have an interest in medical, if you have an interest in music, if you have basically audio, if you have an interest in, say, segmentation. So it's like, now is a good platform. Like everything's been set up for you to go forward and learn about these things nicely. And like we already covered ResNet. So I've got another group going at Weights and Biases, which is the paper reading group. So I'm sorry for like taking this on for longer than usual, but I do want to cover like all the things that were there in my head that that could be left in case like if we stop the fast book reading group here. So if you go to this paper reading group and you see this like again in community events and there's the paper reading group, you can see like there's this master list which contains all the papers that we've discussed so far. So if you want to look at EfficientNet V2, there's like this paper, there's a YouTube video, same for DenseNet. So just recently we did DenseNet. For ResNet, we did the ResNet live coding. So you can go to YouTube would be a nice place for this. So if you go YouTube and you search for the Weights and Biases channel, so if you go Weights and Biases, so you can see this Weights and Biases channel. And then if you look at the videos, you can see there's like all of these different videos and playlists that that would serve this purpose. So in videos, you can see there's like the PyTorch reading group, which is hosted by Sangyam. Then there's the DenseNet reading group. Then this is live, and then we have a live coding session on ResNet. So there's like all of these things where, again, these are these resources that are going to continue. So if I think I have spoken about the paper reading groups before, that this is, again, a great time to get involved in reading papers. And I know for a fact that some of you have been writing blogs. For example, Vinayak did reach out to me and he's written a blog about DenseNet. I know Ravi Mashru, he's reached out to me and he's written a blog about, I think, fixing the fixed res paper. So I'm really, really excited to see all of that progress. So with that being said, I think I hope that I'm able to justify this decision of why like stopping the fast book now would be ideal. So with that being said, I still have some closing remarks, which I will do towards the end. But with that being said, let's quickly start off with application architectures deep dive and cover off what I have to cover off here. But let me just go to the forum post and just see if there's any comments. Oh, thanks, Liam. Yes, this is the PyTorch Reading Group. Cool. So with that being said, let's get started with the architecture details. So with architecture details, now with architecture details, what you will see, and this is something that we know, is you pretty much, oh, sorry about that, 1 second. You pretty much have an input image, and this input image is passed through the model. And the model can be divided into two things. One is the body, and the other thing is the head. So for those of you that have been attending the ResNet and DenseNet paper reading group, this would come, like this is something that I've explained there already. So if my input image is say 3 by 2 to 4 by 2 to 4, which just means like 3 channels, red, green, blue, and 2 to 4 by 2 to 4 is the height and width. Then there's the model in itself, like the model architecture that we use, like ResNet, DenseNet, this can be divided into body and head. And the benefit of thinking of deep learning models as having a body and a head is that you can pretty much do something like this. And this is something that we covered off in chapter 1. So when we were doing pre-training, what we did was we cut off the head, if you remember, when I was telling you about like using pre-trained weights. So what you can do is you can cut off the head, because remember when we were learning about what deep learning architecture really learns, we saw that the earlier layers, so there's like early layers, middle layers, and then there's like these later layers. So these are later layers, early layers, and then something in the middle. So we saw that the earlier layers are the ones that learn like really low level features like diagonals, edges, circles, and the middle layers learn on top like some faces or like eyes, eyebrows, and things like that. And then the later layers are the ones that learn the most specific things to the data set. So if you're working on ImageNet, or better yet, if you're working on pet breeds, data set, then the earlier layers will learn something like edges, diagonals. The intermediate layers will learn something like fur, or like dog eyes, or cat paws, or like those sort of features. And then the later layers will learn like we'll accumulate and join all of these and learn all about like, okay, this is what a dog looks like, this is what this specific breed looks like, and so on. So what we do in transfer learning, or pretty much in model architectures, is we cut off the head. So what is this head? In a way, you can think of the body as a feature extractor. So what that looks like is when you have your input image and you pass that through the body. For let's say you're using a ResNet. So then if you have an input of like 3 by 2 to 4 by 2 to 4, again, if you've attended the ResNet paper reading group, you already know that as we go deeper and deeper into the ResNet architecture, what we do is we increase the number of channels and we decrease the spatial dimension. So the output looks something like 512 channels and 7 by 7. So if it's like this big, it just becomes like really small, but has a lot of channels. So it looks like something like that. Something like that. So these are like 512 channels, and then 7 by 7. So you have like something that becomes really small. So the number of channels increases, but the spatial dimensions become really small. So in a way, why this is called as a feature extractor is because now if you use like a pooling layer, then you can get this as a 512 vector, right? We already know what pooling is. So I can represent, in a way, what I've done is that I've passed this image to something called the body, and then that's given me a 512 long vector. So I can represent an image as a 512 long vector, right? So this 512 could be the feature representation. Feature, I'm just going to call it feature. So in a way, I've like represented the whole image as a 512 vector, and I could do this for all the like however many images I have. If I have another image, I pass that through the body and I get another 512 vector. So like I can represent things as vectors. So in a way, the body is the feature extractor. And then what happens next is you have something called a head. And the head is responsible for doing like different tasks. If you basically for all of deep learning, you want this, everything before this is pretty much the same, but the head is what changes. So if you want to do object detection, you use a different head. So if you could do object detection, for which you'd use like a bounding box head, or like a you could do segmentation. You could do just classification. You could do multi-label classification. So this is like all those sorts of things, multi-label stuff. So it's like all of these different things that you can do by just having a, sorry, one sec. There's all of these like different things that you can do by just having a custom head. So this is the main point that I want to make about architectures, is that a complete architecture can be just separated into a body and a head, and you can keep the body, and as long as you keep updating the head, you can do more and more things. And this is something that's been explained in the CNN learner part. So whenever we create a CNN learner, remember when we were doing like segmentation, we again used the CNN learner class, and when we were doing classification, we still use the CNN learner in FastAI. So the reason for that is because FastAI, what it does underneath is that it updates the head. So for segmentation, it would use something called a segmentation head, and for classification, it will use something called a classification head. Are there any questions on like this, just this basic? Oh, thanks, Ramesh, for this great feedback. Okay, so that's just the basics. That's just the basic. So now let's get started and start looking into what a CNN learner is. So in PyTorch, now what I also want to do is I want to make sure that you're able to read and write good quality code. So there's like different ways of doing this. There's again, you could use Visual Studio Code, or you could use Vim. So in this case, let me just show you how to use Vim. So I'm in FastAI. I guess I need to close off this, and that's when this will work properly. Yeah, there we go. So first, let me show you Vim. So let's say you want to learn about the source code of CNN Learner. So that's another thing that we need to start looking into, right? So I can just go here, I can press Vim, and there's something called ctags, and I can say tag CNN Learner, and that will take me to the CNN Learner source code. So like this is a really good way. Vim is a really good way to look at the source code, and another good way is to just use VS Code, which is another great way, which I've shown you a few different times before. I guess this is taking some time to open up. It's opening PyTorch image models. That's from yesterday, I guess. But we need FastAI. Okay. So again, with CNN Learner, what you do is whenever you're trying to create a CNN Learner, again, the point that's being made is every time you use a CNN Learner, so when you use the CNN Learner function in FastAI, what it does is it has something called a model meta. So whenever you're using, like, whenever I say M equals CNN Learner and I pass in like my ResNet 50 model, what that does is, first off, it will use this something called model meta in FastAI, and this model meta has information about where to cut the model architecture. So again, this is for transfer learning. So as I've said, you can just have a different head every time, and having a different head means you cut off the architecture like this red thing here. That's cutting off the architecture, because the whole architecture looks something like this, and then you just cut it off and you divide it into, you keep the left and you get away off the right, and you just replace it with any new head that you want to use. So there's this dictionary called model meta, and if you look at this dictionary, you can see like this dictionary has been defined for all of these various different models. So there's like For DenseNet, it's been defined. It basically tells FastAI on where to cut the model, and it basically tells FastAI on like how the split looks like, so like how do you split the layers, and these stats just means like how do you normalize your input images. So now I could just say in FastAI, I could just say something called create head. So if you want to use like when we this is again showing, and this is again going into the details of how things have been implemented. So what you have is when you start with ImageNet, so ImageNet has 1000 classes, right? So what would happen is you have your 3 by 2 to 4 by 2 to 4 input image. When it goes through the body, let's say you're using ResNet 50, the output that you get looks something like 512 by 7 by 7. So this is like the representation of this input image. You apply a pooling layer. Next is pooling operation. So you get a 512 by 1 by 1 feature, and you could just flatten it. So you have something like a 512 feature. So now your whole input image has been represented as a 512 long vector. And then this is what gets passed to the head. So for ImageNet, the head, what it has to do is it has to take this 512 long vector, and it has to output 1000 classes, right? 1000 classes, because ImageNet has 1000 classes. But let's say if you want to reuse the same architecture for pets, then what you could do is instead of using this head, you could use a different head. So you could use a different head, but this time, instead of having like 1000 classes, this just has like 37 classes, because that's how many pets there are. So now you pass this 512 long vector into a different head, and it's able to do pet breeds classification instead of ImageNet classification. So every time like you create a CNN learner and you say, okay, that's however many classes I want, underneath what FastAI is doing, it uses the information from model meta. It cuts the architecture at this specific point. So it like keeps all the layers except the last 2 layers. It cuts it off at that point. So it keeps all the layers except like the last 2 layers, which is just the head. So it cuts off the head, creates a new head like this, and that's pretty much it. Like then you have your CNN learner, which can do a pets classification, and which can do ImageNet classifications. There's like pretty much you just update your head. So I hope like by showing you this example of like how all architectures can be seen as having a body and a head, I hope that I've been able to make those things clearer in your head. Is like how can we use this CNN learner function for pets, and how can we use the same function for ImageNet? So I'll just have a look if there's more questions. Okay, there are. Thanks, Ayam. That's a good one. How to get source code and VS Code? Yeah, as Ayam has mentioned, if you go to if you just search FastAI like that, and you go to FastAI Deep Learning Library, and then as Ayam is saying, now GitHub has this amazingly cool feature. If you press dot, I've just on my keyboard pressed dot, and nothing's happening. Interesting. Oh, I'm not signed in, I guess. That's why. I'll have to sign in. So let me go. Just trust me. Like if I go into my personal here, and I go FastAI, which is just, let's say I'm in the Fastbook repo. I'm logged in now, and I guess now I can press dot. Yeah. So if I press dot, you just need to be signed in into your GitHub account. And then if you press dot, everything will load up in your VS Code. And then everything that you see I'm doing over here in this VS Code, you can pretty much do right here. So you can still do Control-Shift-F to search things. You can still like look at the source code. You can go into clean. You can look at the notebooks and all that stuff. So I'll just close this. Okay, I have a question on head. For classification, we use certain architectures, but for segmentation, we usually have different base architectures like UNet, RetinaNet. Ramesh, you're wrong, but I will tell you why. Just give me 1 sec. Most of the work really is in the data prep. Can you speak a bit about data prep step in object detection? In it, we have locations. So we no longer have 1:1. We used to have the classification or even segmentation, but the architecture might use anchors or other techniques. How do you go about building data set for object detection where each so for this one, while I don't want to go very much into object detection, I do want to give you point you to these two blog posts, which is the annotated DETR and efficient det. So in that one, you'll see like points about anchors, and you'll see points about like this is pretty much cocoa detection data set. So if you go in there, you'll see like the annotated DETR blog post has this data preparation, which just explains everything on how you do data preparation for object detection. So that will give you some insights about that. As far as when you say for segmentation and object detection, we usually have a different base architecture like UNet. So we're going to touch into UNet and we're going to touch into RetinaNet, but actually even these architectures reuse ResNet as your feature extractor. So again, you can look at these things as a body and a head. RetinaNet have like RetinaNet has like these different configs where you can use ResNet 50, ResNet 101, or like different things. And you could actually like use RetinaNet with TIM to have like all these different backbones. Same for UNet. So I think you can still have a look at these things as having a body and as having a head. If that doesn't work, change GitHub to GitHub 1S. Yes, thanks very much. That's a great point as well. So again, what's been mentioned is if I go to GitHub, this one, and if I just call it GitHub 1S, that should load it in VS Code already. There's great points. Thanks for putting these as comments. So that's that. So that's the architecture details. Now, next step is UNet Learner, and we're going straight into UNet. While first, I'd like to, again, it's just that I've written blog posts about pretty much all of these things, so I keep pointing to them because I think they're really good quality in terms of like explaining things from scratch. So for example, in this blog post, if you, there's like in Fastbook, if you go to UNet, there's like this section, which is a somewhat smaller section on UNet, which is just this much. But if you look at this blog post, I've explained everything on how to implement UNet from scratch, and it's all in 60 lines of PyTorch code. So by the time the whole architecture, again, I've got this whole really nice factory production line analogy, and I'm going to use this to explain UNet right now. But if you go through this blog post, you'll see like towards the end, this is what the UNet architecture looks like, and overall, it's all just this much code, which is pretty much 60 lines of code when I counted last. So the whole architecture can be implemented like this, but let me try and explain what's happening in UNet. So in this FastAI, in this part of the Fastbook, what's trying to be explained is like how you can do segmentation. So I've told you like an architecture has a body and it has a head, but then how can you do that for segmentation? Because segmentation is a completely different task. So when we were doing, I think it was chapter 1. So let me see if I can bring that up. There was this really nice visualization on segmentation on Camvid. So I just want to bring that up. Should be at the bottom. Okay, here it is. So for a segmentation, basically the task that you have to do is that for each image, you want to segment every pixel. So you want to say like for this image, you want to say all of these pixels are roads. Then you want to say like all of these pixels on the left are buildings, all of these pixels are buildings, and then all of these pixels are cars. So it's a much difficult problem to do than just like classifying, okay, pets, this is like the pet breed for this image, or this is the pet breed for that image, and something like that. So segmentation is a completely different task. But what the UNet architecture looks like is like this. So a UNet architecture looks something like this, and that's what's been explained in like what happens in the FastAI UNet learner. Is when you create a FastAI UNet learner, basically you could use a ResNet 50 backbone. So you have your input image, which is at this point, and I'm just trying to explain like UNet and segmentation, just exactly what goes on in the specifics is that when you have your input image style, when that goes into it, these two things, like this is just a small block which consists of two convolutions. So let me actually put that in OneNote so I can explain it and pretty much annotate it. Okay. So first, let's just look at everything that's on the left. So just this much, okay? Just everything that's on the left of this line. So you can see this is just like a standard encoder. This is just like a standard feature extractor. So you have your input image. Let's say it's 3 by 572 by 572. Then you apply two convolutions, these are conv 3 by 3 and 0 padding, so there's no padding. And when you apply a conv 3 by 3 to an input of 572 by 572, let me show you what happens. So let's say my input is torch.random1 by 3 by 572 by 572, and I'm applying a conv, which is nn.conv 2D, 2D, kernel size inchan is 3, outchan is 64. Because remember what we're doing is we're going from the input has, well, in my case, I'm taking as 3, they're taking as 1. So let's just keep that the same as the image. Let's just use a one channel image. So you have input channels as 1, but then the output channels are 64. So output channels are 64. I'm just updating that to be one channel. And kernel size is 3. And then let's see what the output shape of this is. The output shape is 1 by 64 by 570 by 570, which is exactly that's mentioned here. 570 by 570, 64 channels, correct? So what can be seen is like these two things in UNet when you're doing segmentation. Both these and these are just two convs, right? So it's this, all of this is like just a block with two convs. So it just looks something like this. It's like a block. You have your first conv followed by your second conv. So I'm just going to call it conv1, conv2, and there's no padding in it. So then this block is repeated everywhere. This block is right here, then that block is there, then that block is there, and then finally that block is there. So you have 1, 2, 3, 4, 5 such blocks of two convolutions. And then as you can see, what's really happening is like the number of channels. If you see, we started with one channel, then we got to 64, then we got to 128, then we got to 256, 512, and 1024. And same, if you look at the spatial dimensions, we started with 572 by 572. We got down to 280 by 280, then 136 by 136, then 64 by 64, and finally 28 by 28. So what's actually happening, and again, this is something I've explained for ResNet and DenseNet paper reading groups as well, is like the standard approach is when you go deep into your architecture, the number of channels goes up and the spatial dimensions goes down. So this is exactly what's happening. And all of this on your left, like all of this, is called the encoder. So just give me one sec. All of this is called the encoder. Oh, sorry. This is just called, I did that again. Try and type, oh, right, nicely now. So this is, all of this is called encoder. Now you could use a ResNet 50, you could use a ResNet 101, a ResNet 152, or any for that matter. But in UNet, what actually happens is then you have like this part is downsampling and then you're doing upsampling, which just means that by the time your feature map is down to 28 by 28, and it has 1024 channels, then you want to go and again take this feature map and you want to increase it back to size where it has like 388 by 388 size. So how do you do that? Like so far we've just looked at convolutions that decrease the feature map size, or at least if you apply padding, then it maintains the feature map size. But how do you go from like a 28 by 28 to 38 by 38, like 388 by 388? How do you increase the size of your feature map? So you have a small, what we've seen so far is you have an input image that has 3 channels, and then as it goes through your model, which is this, I'm just going to call that model, you get something like this, which is now smaller in feature map size, but has a lot more number of channels, right? So how do you take this and go back to doing something like bigger spatial dimensions and less number of channels? Like, how do you do that? This is the question. And so far, we've just looked at techniques that are capable of doing the encoding part, which is this encoder. But we haven't looked at this part where we can increase the spatial dimensions. So how does that happen? Well, in an image, like if you know, every image looks something like this, like it's just represented by numbers. So this is like 0.1, just normalized 0.25 or something. These are just numbers. What you could do is you could take this number and like make this a bigger image like that. And it could be 0.1, 0.1, 0.1, 0.1 here. And then 0.25 is 0.25, 0.25, 0.25, 0.25. So pretty much like you're repeating the numbers at 4 points. Now what you have is like you have it's basically you've gone from, if this is 20 by 20, you've gone from 20 by 20 to 40 by 40. But it's not really very meaningful. Like it's not the best approach to increasing the size. So in this part, there's another approach that's being discussed, and it's called as a transposed convolution. So what you do with transposed convolution is that if your image looks something like this, what you do is you add padding in the middle. So you have something like that. My 0.1 goes here, 0.25 goes there. And what you've inserted around these are a bunch of zeros, like just zeros. So this is just padding. And then the next number comes here, like 0.75 or something. So you've just introduced zeros. And now what you could do is now when you do the convolution operation, then this becomes like 1 pixel, then all of this becomes the second pixel, all of this becomes the third pixel. So pretty much like you've increased the size of your feature map. So this is a nice visualization of like how you started with a 3 by 3, so you can see like the blue dots are the 3 by 3 input image, but the actual output that you get is like a 5 by 5. So you've increased the size from 3 by 3 to 5 by 5, and this is the UNet. This is like the upsampling. So in UNet, then what you do next is in this upsampling part, you apply these transposed convolutions, which is called as upconv. You apply these upconv, so you start with 52 by 52, and when you apply upconv, you have 104 by 104. Then you decrease the number of channels from 256 to 128 to 64. Similarly, going from 100 to 200, from 196 to 392, and so on. So now you're doing the upsampling part in UNet. But one thing that, again, the researchers noted at this point is that it's not just enough to apply upconv. What you could do is you have the feature maps on your left. You pretty much use a skip connection, but this time all the way to the right. So like you're adding the same feature map size. And this, my friends, this architecture is the UNet architecture. And in FastAI, I did want to like spend more time on UNet. But again, if you now go through this blog post of UNet, I've only explained this very briefly, but if you go through this blog post, all of this would be explained really, really nicely. And you can see like this factory line analogy that I've used, where I say when you're going down the factory line, everything is like an assembly point. And when you're going down this yellow factory line pipeline, what's happening is that you're pretty much downsampling, because you can see like all of this on the left is downsampling. And when you're going down the orange pipeline in your factory, then you're pretty much using upsampling. And then you can see like how the assembly station for yellow looks like. It's pretty much looks like this, conf 3 by 3 followed by conf 3 by 3. And you can see how the assembly block for decoder looks like you have the features, but you also get the extra features from the encoder, and you concatenate them, and you have conf 3 by 3 followed by a conf 3 by 3. So I hope that explains UNet in a lot more detail. So if you have any questions about UNet, now would be a good time. But otherwise, that's architecture details. I did want to spend more time on natural language processing in Tableau, but for natural language processing, again, we have a, I haven't touched natural language processing for a reason, is that if you haven't heard of Hugging Face, you should. So Hugging Face is this place where it's like it's now kind of been the central place for natural language processing and transformers. So they have a huge number of models. If I go on models, you can see like this is just a small number, but you can look at token classification, text classification. I forgot the amount of models that they have. I think it's like a big number of models that they have and serve. And you can see there's like resources, data sets, there's good documentation on this. And if I remember correctly, there was if I go to community events, there it is. Okay, it's locked. But there is a Hugging Face and FastAI study group as well that was hosted by Wits and Biases. You can find the actually, if I go here, just on YouTube, and I go to Weights and Biases again. So if I just click on this, maybe it won't open the video. And if I go into playlist, I think there should be, here it is, 1DB study group, FastAI with Hugging Face. You can see like this is the FastAI Hugging Face course. The Hugging Face course that was hosted. And I know Sylvain was a part of this. But I think this would be a great place to look at NLP. And another NLP course that I would recommend is by Rachel Thomas. So Rachel Thomas NLP course. I've forgotten what it's called. I think it's called, oh yeah, A Code First Introduction to Natural Language Processing. So let me put that on the forum. So anyway, the point that I want to make is like this already existing resources. Oh, Sayam already posted this. Hey, Sayam, I got you covered. NLP course. So again, this is a great place to start with NLP. It introduces everything. If you have a look at, I'm trying to find lectures are in this playlist. There it is. And in that playlist, you will see like there's everything. It does topic modeling. It does what is NLP. It starts from the basis. It does naive Bayes, transfer learning, ULM fit, RNNs, sequence to sequence, GRU, and then introduction to the transformers and transformers language translation. So I think this is really an underrated course, but it's a really wonderful course. And this is where I started my journey with NLP. And then once you're done with that, switch over to Hugging Face. Hugging Face is the place for transformers to learn about these papers, like the attention is all you need paper. And then there's like GPT-2. And I also have another resource that I like to share on GPT-2, which is this one, annotated GPT-2. So when you get to transformers, I'm posting all of these. Once you get to transformers, here is another resource. So that's another resource. So that should get your NLP pretty much sorted. Like if you follow these resources, that should get your NLP sorted. And then we are left with Tabular. Tabular, I think Zach has been doing some wonderful stuff with Tabular. I don't remember if there's resources that I can point you to straight away, but let's see. Muller, Tabular, deep learning. I think there's something he's got it covered. Sam, help me here. Do you know a good Tabular course that I think it's part of? It should be part of running Walk with FastAI. And where is that Walk with FastAI? Walk with FastAI. I think that's part of this. Okay, there it is. Walk with FastAI Tabular, and you'll see introduction, classification, using Tabular Pandas extension, autoencoders, and all of that stuff. I think this is a great place to learn about more about Tabular things. So I'm going to post this again in the forums. Tabular. That's that. And then what are we left with? Computer vision we've covered as part of Fast AI. Next thing that you'd like to do after this is go to PyTorch image models. So learn about more models. Right now we've just covered ResNet, but go to this repository. I've got TimDocs. TimDocs. Here's another resource. So 2 more resources. Sorry for just spamming the forums, but I do want to on CV. So TimDocs, and we have Tim. So basically, like, these are the places where you learn a lot about a lot of different models. So start reading those papers. Again, do the paper reading group, because if you go to the paper reading group, you will see we're pretty much computer vision heavy. We actually just do computer vision in the paper reading group. So you can see there's like ResNet, DenseNet, EfficientNet, squeeze and excitation network. We've got DETA, which is for object detection, Kite, which is a transformer. EfficientNet, we do Convit. We had Stefane join us from Facebook. For MDETA, we had Ashwarya Kamat join us. And then there's like other things that I could point you to. Is more blog posts, but I'll just add them to the forums. So that should be a complete list of things that can be referenced. I don't think I'm missing anything. If there's any questions, like if there's any specific resources that you'd like me to mention, please just post them in the forum thread. Because am I missing something? I think that should get everything covered. NLP is covered, computer vision is covered. Segmentation, I think there's a great repository, yeah. PyTorch segmentation models. Segmentation models PyTorch. So this is again a great repository. I'm just going to push that there. Segmentation models PyTorch. It's another great repository. So I'm just doing a dump of like all of these different resources, so you can like go and take your pick and find your topic of interest and carry on. But now coming to the closing words for Fastbook. Again, this is an emotional moment for me, and all I'd like to say to everybody who's been part of this journey this long is a big and massive thank you, because I think like most of you have been a part of this journey for 15 long weeks, which is more than 1 quarter that I think of it. So we started off with no knowledge of deep learning, and I hope that we have come to a point where you have some knowledge of deep learning, at least. Like there's things that have improved from where you started with me in this journey, and I hope like some things have improved. And I would like to thank the community, like all of you that have been a part of part of Fastbook, and you've been writing blogs week after week, and you've been doing. And I think Sayam hosted a community hangout group, and he highlighted the work from you guys. So Vinayak was there, Ravi was there, Ravi Mishru, Ravi Chandra. Am I missing people? I think I can't, like, if I start taking names, like it's going to be a massive list of like 15-20 people that have been part of this journey from right from the beginning. And the only words that I have to say is thank you, and you can reach out to me anytime and whenever you feel like you've got a question for me. So my Twitter actually is twitter.com. I think that should work, right? Yes. So I'm just going to share where you can places where you can reach out to me is Twitter. That would be a great place. LinkedIn. Oh, that's not found. Let me try my personal, because I think it's stored there somewhere. LinkedIn, there we go. I think I've missed the community thread. Where did that go? Ah, there it is. Fastbook Reading Group and the P15 thread. And I was writing this. So these would be places where you can reach out to me, is like the Twitter and LinkedIn. And again, this is where I like to stop. But if you have any questions, Durga, yes, this is the last study group session for now. There's as you I have pointed to other resources like the PyTorch Reading Group and NLP resources, and I think Sanyam is doing a great job for the PyTorch Reading Group. Thank you, Ravi, for such nice words. And look forward to seeing you in the paper reading groups. Yeah, we're going to do. So what we're doing as well as part of paper reading group is that I've started doing live coding sessions, and in those live coding sessions, I'm pretty much coding architectures from scratch. So I heard we had the first one where I wrote our RESTnet architecture from scratch, and that's all part of the. If you go community events and you see paper reading group on the forums, which should be here, and you will see there's this RESTnet live coding. So you can see this like RESTnet live coding. You can find I think the YouTube link right at the top. So if I go actually at the top. There's this stream, you can see there's that live coding stream, and click on it and you'll find that link. This will always be remembered as a favorite fast AI. Thanks, Ayam. Really appreciate that. Cool. I guess that's where we will end things today, and that's where we will end the Fastbook reading group at Weights and Biases. And I do look forward to seeing each and every one of you in all of these different events, and just reach out to me on Twitter or LinkedIn if you have any questions, or I can be of help at any time. So thanks very much and goodbye. Oh, thanks, Matt, for the. Thanks, guys. Really appreciate this. Thanks very much. See you, and yeah, see you in the paper reading group, I guess. Bye.